All right, so Robert Heath, this is lecture number 13 of the Wireless Communications Lab. So today we're going to continue talking about dealing with intersymbol interference channels or frequency selective channels. And first off, we're going to talk about least squares channel equalization. Now, the last lecture we talked about least squares channel estimation. So in this part, we're going to use the channel estimate to estimate the coefficients of a filter that will help remove that channel. And then we'll see a slightly different twist on the same problem where we estimate this filter, which we call an equalizer, directly from the data. And so you should be able to derive and compute those coefficients here without a channel estimate. And then after that, we're going to continue into the frequency domain and look at here, why is it challenging to equalize in the frequency domain in the first place? And then we're going to build up another mathematical approach for equalization based on the discrete Fourier transform, which we review at the end of the lecture here. And this is the discrete Fourier transform, not the discrete time Fourier transform. So this is a different transform that will turn out to be very useful from a signal processing perspective. Okay, so with that, let's get started here. Just a quick review of where we are at right now. So let's look at the, let's start off with this right here. This is like the idealized AWGN transmitter and receiver that we've been considering up until about a week ago here. And so you can see there's symbol mapping, digital pulse shaping, amplification, RF. And then on the receiver, that there's oversampling, match filtering, downsampling, detection, and demapping here. And that was our idealized receiver. And so what we've been focusing on now has been adding complexity to the receiver to deal with a more complicated impulse response between the transmitter and receiver. On linear equalization. And we might have a problem on decision feedback equalization later. So generally speaking, so an equalizer, as we use the term here, DSP term, is a filter that removes frequency selective distortion. And so this is used in a lot of different signal processing problems. The most common one is used in audio, where you might be correcting for poor frequency response of your headphones or your speakers or the environment that you're in. Most home theater audio systems now come with some mechanism for training and estimating and implementing equalization. So in the old system, you could modify the treble, the bass, and the mid-range, but now systems implement much more complicated filters, and they can measure the impulse response of your room and then use that to create a good audio model. So we're going to use this concept for equalization of our multipath channel. And so the idea is that, so we're starting off with the input-output relationship that looks like this here. So we're going to consider everything in discrete time at this point. And so we have our channel here corrupting our transmitted symbols, added by noise here. And so from a discrete time signal processing perspective, this filter is distorting our sequence of symbols here. What we want to do is we want to construct, and we're going to focus on finite impulse response filters, an FIR filter with coefficients. I'm going to call that filter F and give it coefficients k equals 0 to, let's say, I guess I use in the notes n sub d. Sorry, not n sub d here. This is going to be capital. All right, let me look here. Oh, all right. I've changed the notation around in different places here, but I'm going to use L sub f here. L being the order of this filter here, f being the fact that this f here, to distinguish this from the L over here. So what I'm going to do here is I'm going to construct this FIR filter such that when I filter the sequence of observations y sub n here, so I'm going to take my f of L, convolve it with y, and what I want is I want to get rid of the effects of this h here. And I'd like to get rid of some noise too. That turns out to be hard, and we're not going to include that noise in our formulation. What we want to do is we want this filtering operation to give us out essentially one of the symbols that we sent. But instead of requiring that we get S of n, we're going to be a little bit flexible and require that instead we get a delayed version of what we transmitted here. So this n sub d is going to be a fixed delay here. FIR filter. And this is essentially, it's a least squares inverse filter, because what we're trying to do is we're trying to invert the convolutive effects of H with F. So this is an inverse filter here. So we're going to consider this least squares, I'll just try this here, least squares error here. So I'm going to have some function J, let's call it J of F. Here, that's a function of the unknown filter coefficients and the delay. And so that squared error is going to be, so let's look at this right here. If we convolve this filter here that has LF plus 1 taps, and this filter here that has L taps, L plus 1 taps, the resulting filter should have length LF plus L plus 1. So it goes from 0 to L plus LF. So we have the squared error terms that sum over all the possible values. Let's put a delta of n minus nd here. Minus. So we're just rewriting this as a squared error term. I'm going to put this here. Sum over L equals 0 to LF. F of L. H of n minus L. And then I put the square here. So this is our squared error function. And then we want to find the filter coefficients that minimize this thing here. And so I could rewrite this, in a couple of different ways here. So what we're going to do is we're going to effectively solve this as follows here. So we're going to solve this. We're going to find the minimum squared error for each possible value of nd, and then we're going to find the one that has the lowest error. So nd sometimes is just fixed. You could just fix it at 0. Sometimes you could optimize over it. So in a sense, it might be better to write this like this, as we're sort of conditioning on this parameter here. Okay, now the other slight wrinkle here is the h. So we have h right here. Remember that we don't know that perfectly here. So we're going to use our estimate of h to derive our estimate of f here. So we're going to use h hat least squares in place of h. And then we're going to solve for fixed nd, possibly optimizing over it. Okay, so now the trick is essentially write this into a set of linear equations. We know the answer when we get to that point, so we're almost done, it turns out. So what we're going to do here is I'm going to put this here. So basically what we need to do is, so we have the convolution here, we have this delta. So this delta, when we enumerate all these values from 0 to LF plus 1, that's going to give us the b part of the equation. So this is our least squares set of equations here. What we're going to do first is this delta here. So this is 0 everywhere except for the place where nd is equal to 1. Otherwise it's 0. So from a vector perspective, this is in the nd plus 1 position. If nd is 0, then this will be 1 and then all zeros here. So this is just our, we're going to call this E sub nd. And we call that E because E is usually used in this way to denote a column of the identity matrix. So it's just it's a common notation in matrix theory. Okay, so here, remember, this is our unknown here. Our unknown is going to be the parameters of the filter here, f. So we're going to put f0, f1, down all the way through here, f of LF here. That's our unknowns. And then now all we have to do is fill in the terms of this convolution here. Now this is a little bit different than the problem that we had before, but you could solve it in the same way if you don't see the solution here. But you can remember, an easy way to see the solution is, okay, so we have f0 through f of L. And remember the old flip inside with the convolution here. So then we're going to flip here and have h of 0 through h of L here. We're going to slide this over here like this. And so we start off in the sliding here with h0 and all zeros. Then we have h1 and h0 and all zeros. Continuing on down through h of L. Then as we get to the end of the convolution, it starts to trail off. And then we end up with this matrix here. So this is our matrix H here, which I could put a little hat over it because it's composed of our channel estimates here. And so this is a nice structured matrix. It's a Toeplitz matrix. It's got zeros here. It's got a big quadrant of zeros here. And it's got constant diagonals that consist of terms of the channel here. And you can show that as long as any of these is non-zero, this channel here has full rank, this matrix. So that's just one interesting property of it here. So what we've done here is we've just built up a set of linear equations. And now we can plug in the least square solution. So we get f hat equal to h hat star h hat inverse h hat star e of n d here. And so that's our least squares equalizer solution. So look at what's happening here. When you multiply through this h by this e of nd, what you're going to do is you're going to pick up one column of this h star here. So essentially, we're going to pick up one of these columns of this right here, and that becomes our vector. And then we're going to multiply that through by this this inverse here. So I mean, that's essentially it. Couple things here. Let me just talk about the rank and the ND optimization here. So first of all here, so the dimensions of this h. So h hat is L plus LF plus 1 by LF plus 1. This makes sense because the output of the convolution is, as I mentioned before, the length, the sum of the lengths minus 1. And then this is the unknowns here. So this thing is always tall, unless L is equal to 0 or it's always tall. So there's no exact solution possible unless L is 0, but then that's the flat fading case, which is boring. So H is tall if L is greater than 0. H hat is full rank if any h of L is not equal to 0. Now that said, yeah, it still works. It should still work here. Okay. And this I'm not saying is obvious, by the way. So this is a result from random matrix theory here. So the last piece is how do we optimize this ND parameter here? Well, what we can do with the ND, if you wanted to optimize it, is we could look at this cost function here, which is an integer cost function, and we could just substitute in for this value of END minus H hat, F hat here. And for that hat here, I will put the, let's say, I'll put an ND up here. Squared. And then you can just rewrite that as, finding the norm of this identity minus h hat star h hat inverse h hat star e of nd here. And then so find the optimum, which maybe I'll call nd hat. It's equal to the arg min of j of nd here, searching for nd equal to 0 through. It's not infinity, because you can have at maximum a delay at the end here. So it'd be 0 to L plus LF here. You can find the minimum here. And so if you think about it right here, what this is doing here is we're going to pull out, what this E does is it pulls out a column of this product here. So this is an identity minus this stuff here. So we're going to try to find the column of this matrix here that has the minimum norm. And that gives us the smallest error. And that would be the optimum delay, should you want to have one. Okay, so that's essentially it here. Now I'm going to just draw the updated block diagram based on this idea here. So the updated block diagram would be, we still have the oversampling by, some symbol fraction of the symbol period here. We still have that match filter at the receiver. We haven't gotten rid of that. We still have the symbol synchronization. We still have the downsampling. Right? So we have all of this because all of this was at the beginning of when we derived the discrete time signal y of n here. So this was like all there already. Nothing new. So now what we're going to do is we're going to put in a block here, which will be our equalizer. And as part of that equalizer, we will have, let's say, equalizer computation here. And then let's call this channel estimation down here. So compute our channel, compute the equalizer, and then use it to filter here. And so this, you may actually not need this arrow here. Depends on which strategy you use. So I'm going to actually delete it here from what we need so far. And then we're going to take that output here, and then, oh yeah, we have a delay maybe. So we got to correct for that delay by just shifting our symbols with a z to the nd here. Implement that delay there. And then at the output here, we have the symbol detect. And then we have the symbol mapping operation. Ooh, almost barely fits cleanly. Yeah, okay. All right, and so that's what the receiver looks like so far. Now, a couple other questions here. One is, why do we need this match filter here? We actually, strictly speaking, don't really need that match filter there because we are doing equalization anyway. So it's not a big deal to not have it. But in the case where you don't have much of much inter-symbol interference, it would be nice if the system simplified back down to the flat fading case. And so in this way, if you have a channel where there's not a lot of frequency selectivity, we still have something that approaches what the optimum receiver structure should look like. Another question would be, why do we need this symbol synchronization and downsampling? Well, this is kind of for the same reason that, a lot of times these multipath channels are sparse. And so there will be a lot of benefit from an SNR perspective to oversampling and taking the right sample. And this is done in most commercial receivers these days. So other issues here. Another one, why can't we take this and push it over here and combine it with this filter? So why can't we do that, or can we? Anyone want to comment on that?
The number of samples there are too high, so there will be unnecessary computations because we are downsampling later. So
Yeah. So that's a reason not to put it there, is the computation is higher. But it turns out, and I even have homework problems on this, that there's actually no reason you couldn't do it there. I mean, practically, you may not want to do it if you oversample it by a factor of 100. 100 times more complexity would be bad. But if you're oversampling, say, by a factor of 2, it can be a lot better to equalize over here and then downsample here. So it is actually possible. It's just maybe complexity reasons we might not want to do it. So there's some interesting stuff that can happen if we squeeze this over here. And you can imagine that creates a really fun homework problem to do, because you have to formulate, actually, it's better if you formulate it as a filter bank, so then you have an interesting optimization involving multiple sets of filters. And anyway, so you can solve it all using least squares. You have to stack and create this really cool looking matrix. But I'm getting ahead of myself here. Yeah, that's a great homework problem. Yes. I must have it in the book. I should give it to you. Okay, any questions on this setup here? Least squares, estimation? Yeah, you guys are up for it? Yeah. Yes. It'll be good. Any questions on just the equalization, or old question on estimation, or question on least squares, or the receiver structure here? I guess no. It's super clear. Oh, question in the back.
This might not be that important, but you said that you need an IIR filter to invert an FIR filter?
Yes.
Why is that?
Because if you think about it in the Z domain, an FIR filter is going to be all zeros. And so if you wanted to create, so if you have a filter, let's say h of z here, that's z minus a1 through z minus a of k here, right? And you want to find another filter such that h of z, g of z is equal to 1, then, which is basically what we're doing here. I mean, the ideal filter would be something that looks like g of z equals 1 over z minus a1, z minus a2, dot, 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 z minus ak. And that's an IAR filter. It's poles. So if you convert that back in the time domain, it has an infinite impulse response. So that's the basic reason here. Now, there is something very tricky that if you were to actually do this equalization over here, there's maybe a way to do it with FIR perfectly. But I'll leave that for your thought for another time, another class. And so, just as a follow-up here, I mean, we could implement an IAR equalizer, right? We could come up with, you wouldn't use this least squares form, but we could come up with a recursive equalizer structure. I mean, it's not impossible. It's just that the reason that we typically don't do that is that we're often going to communicate using packets that are short, so maybe 100 symbols. And when you have an IIR filter, you have all this memory in there. And so if you stick in only 100 symbols, it may not have enough time to really, to settle and get rid of. Well, actually, I mean, it should get rid of. It depends, but you'll end up with sort of a transient effect at the beginning there. I don't know. That's maybe not a good reason here. There's probably another good reason why we don't do it. I can't think of it now. Can you think of a reason? I was thinking this would be a great new homework problem. Estimate IAR filter coefficients using least squares. See, now I'm torn between the filtering before the downsampling and this new problem. Man, it's so tough. Mondays are hard. All right. Let's take a short break here. Eyes glazing over. Monday morning. Okay, so I was pleased to see on Engadget today, you can't probably see this picture very well here, but this is the LG's new announcement here, the LG Flex. So last Wednesday, I spent a few minutes talking about Samsung's new announced curved phone, the Galaxy, what was it, Galaxy, was it Galaxy G or Galaxy Curve? So it was curved like a, in a totally different way. Where's my phone here? I mean, the Galaxy phone was going to be curved so that it would rock like this. And this phone is going to be curved so it rocks like this. So, yeah. Got 2 of the 4 possible curves here so far. Any comments on this here? This is what it looks like as a side view here. I mean, from a perspective of being a phone that you hold to your head, I mean, having the curve seems to make sense to me, like this, if it's big enough. But, you know.
Does it make it more fragile?
Maybe. Yeah, could. I don't know. I mean, but they're also selling that this has got a special flexible screen, so maybe, I don't know. Why would it be more fragile? Like, you just tend to drop it on the corner more often, or?
I don't know. I guess I think that, you know, all the impact would be like on a smaller area. Basically.
Yeah. Well, it seems like, yeah, I don't know. Yeah, that's right. Yeah, but then again, I mean, if you drop it, you know, it's not like it ever lands perfectly flat. So, but yeah, it seems like you're going to more likely hit the corners. I don't know. Okay, so we've seen like it coming out like this, and we've seen it curving like this. Is there some reason it should curve the other direction? In either case, I'm just wondering here. I mean, these are both kind of concave. I mean, should we have the other convex option?
Curve in two directions.
Be like totally asymmetric, or like curve from corner to corner? Oh, yeah, okay. Now that actually is interesting, because if you're right-handed, it could curve like this, right? Yeah. No, or maybe it should curve like that. You might be onto something here. Should try to patent that. Curved phone, diagonal curve. I mean, the best case would be if it's flexible, so you can curve it however you want. I mean, it seems like if it was curved out, I mean, I'm just trying to think of some example where you're sitting across from someone and you want to share your screen somehow.
Maybe like wearing it on your arm. That would be good.
Yeah, like the watch, the Galaxy Watch that was curving out. Yeah. Yeah, I don't know. Well, we'll see. I guess the market will decide what of these various curves end up being more successful here. But that's good. It's good that there's some fresh thinking happening here among the different companies, you know. So next we're going to see, like, you know, an S curve or something even more exciting. That would be cool. All right. That was, wow, really exciting. Now, back to something almost as exciting. Least squares. Wait a second. That's the wrong one here. Where did I get that? Find this here. Oh, yeah, sorry. I'm reusing some of my old slides. That's it. Okay. No, wait, that's not it either. Shoot, where did it go? No, here it is. All right. Least squares equalizer, directly from the data. Okay. I find it somewhat odd that we estimate the channel and then we estimate the equalizer. So I just wanted to show you that there's a cute trick that we could use to estimate the equalizer without estimating the channel. So this is just something that I find kind of cute more than anything. So you should be able to do this computation here. So let's look at this now here. So effectively, okay, so this is least squares from the data here, which I should say is from the training data. Okay, so let's go back to this model that we started off with here. So we had that we want our equalizer to give us out something that looks like a delayed version of the input when I convolve my observed sequence with that filter here. So the observation here is that why don't we just use this directly to build up our least squares set of equations here? Because we know, so if we know that we have training, so we know that, let's say, S of n is equal to our training sequence for n equals 0 to nt minus 1. So now use this directly to build a least squares solution here. So again, we're filtering y and producing s, but we know several values of the s because of training. So now we're just going to stack everything together and build a big fat matrix here. So let's look at the squared error here. So the squared error, actually we have to be a little bit careful with the squared error, we think. No, actually we don't. It's okay. So we can write some squared error function here. You can write it like in a similar way as before. Where we're going to sum. Now here, what we know is the values of the training from 0 to nt minus 1. So we're going to sum from 0 to nt minus 1. That is a minus 1 somewhere, yes. Absolute value of, sorry, this is going to be t of n minus the sum from L equals 0 to L f of L, y of n minus L, absolute value squared. So this is like our squared error function, and then, oops, sorry, I forgot the nd here. Okay. Okay, so with that here, now we're going to write this in matrix form. Now let me think for a second here. What have I done here? Yeah, sorry. What I'm going to do, okay, yeah, this was what was bothering me here, because if I put the nd here, there's values of the training that I don't know, which is a problem. So actually what I need to do is I need to rewrite this as, so I'm going to replace n minus nd, I'm going to put the nd over here. So I'm going to rewrite this as s hat of n is approximately equal to 0, sum of 0 to LF, f of n L, y of n plus n sub d minus L. So this is this signal after that advancing operation here, so we can shift it around here. And so now I'm going to write the squared error using this nice form of red whiteout that I have here, like this. I'm going to put this as n plus n sub d here. Okay. Now this form up here I had would work, but you would have to you couldn't sum over all the values of the training because you can only sum over what you know. So that's essentially why I'm changing it here. I could also change the indices of the sum too. Okay, so with that, now all we do is just build up this set of least squares equations yet again. Wow. It's a lot of distortion up here. So let's put over here, this is going to be what we know. That's t0, t1, down through t of nt minus 1. So that'll be our t vector there. What we don't know, the coefficients of the equalizer, f0 through f of LF. That'll be our f vector. And then all we have to do is populate this big fat matrix here. So to populate this, what we do is we look at this convolution here. So we start out with like 0 here. So if we started out with 0, we would get sum of 0 to LF, f of nd of L, y of nd minus L here. And so then we just put that in the first row here. So then that'll be y of nd dot 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 y of nd minus LF here. And then just continuing on, we get down here to y of nd plus nt minus 1 over through y of nd plus nt minus LF here. And we're going to call this here y. We'll put a little nd here just because the nd is a function of the y here. So we get out that f hat is equal to y sub md star, y of nd inverse y star times t. And you can do a similar trick to optimize over the nd as well here. So can optimize over nd. Okay, so here, let me just, I guess, put some comments here on this direct versus indirect here. So first of all, in most systems that I know about, and keep in mind that a lot of what we're talking about here, like the equalization, isn't described in a standard, because it's left up to the implementation. So it's very hard to actually figure out what Qualcomm or Broadcom or a company is doing on their chip, because it's just proprietary information. So I don't know for sure what people are using, but to my knowledge, this cute idea that I've shown you, they actually don't use it that much here. But the advantage of the direct approach is that you avoid this chain of estimation error. And so what I mean by that is that if we take the indirect approach, we estimate the channel, and then we estimate the equalizer. The estimation error is sitting inside our channel estimate, and that gets inverted to produce our equalizer, right? And so somehow we're going to be amplifying the error by doing that. It's like a two-step process. So here we're avoiding that amplification. So that's like the main benefit here. Another benefit of this is that so a disadvantage of the direct method is, let's look at the dimensionality here of this y here. So the dimensionality of y is going to be nt by LF plus 1 here. So to make this tall, LF has to be smaller than nt, right? So to be tall, you have to have LF greater than or equal to nt minus 1. Sorry, less than or equal to nt minus 1 here. Whereas we didn't have that restriction at all in the other case. You know, you could take your channel estimates and you could create a 1,000 tap FIR equalizer if you wanted to, not a problem. But here, the length of your equalizer is limited by the amount of training data you have. And so that's an advantage of the indirect method. This indirect method can design equalizers of arbitrary order. And finally here, the channel estimate may be used for other purposes. So that's an advantage of the indirect method. And it turns out that, you know, the system itself derives information from the channel estimate. For example, the average received signal strength that's used in link adaptation, link layer control. It can be used in scheduling. It can be used for many other purposes here. So, so the indirect method is a bit more flexible, but the direct approach, if you were designing a small equalizer, should give you better performance, I think. Now, we'd have to really study this, we'd have to analyze the estimation error, and that would be a bit more work. But I think this is just sort of another cute application of least squares here. So any comments or questions on this here? So to give you a hint here, if you wanted to equalize before the downsampling, this would be the approach that you would take here. Would not want to estimate the channel there. You could, but this would be a better approach. Yes?
What about the training data? Is that bias in the way of the estimator?
Well, the training data definitely influences the quality of whatever estimate you get. You know, and so what you'll see on the homework, I guess that's due this week here. Is that this week we have sequences? I think it's this week's homework where you play with some sequence properties. And so the training data in all cases affects the estimate. But generally speaking, if you were to use a random training sequence, it wouldn't be too bad. It's just if you try to use like a very simple training sequence, like all ones or alternating 1 and -1, that it might not work well. But to see exactly where it fits in, it's a little bit harder to do. I mean, we have to do some statistical analysis to see like what is a good training sequence and how it fits in, and that doesn't work with what we're doing right now in the class here. I don't know if that's too much information, or maybe I just talked long enough so you forgot the question. Yes. All right. Exactly. That's what I was just hoping for here. Do you have a question?
I was just thinking about like as it relates to like machine learning, basically doing a very similar thing.
Right. I mean, this is
your training data is like really important. Here's a little bit different.
in the so the way to see the value of the training data is if we try to estimate the channel. There's a covariance matrix that we essentially empirically estimate that consists of the training that we use for the channel estimate. And that matrix should be ideally kind of close to an identity matrix, which means that you should use training sequences that are sort of uncorrelated in some sense here. And so if you think about this from a system identification perspective, which also has relationships to machine learning, I mean, if you're trying to identify a linear time invariant system, if you stick in a sinusoid, what do you get out? You get out the eigenresponse of the system at one frequency. So you can't estimate the channel by sending it, you can't estimate it by sending in one sinusoid. But if you send in a sum of a whole bunch of sinusoids, then you could decompose that and build up enough information to estimate the channel. And a sum of a whole bunch of sinusoids would be something that looks kind of like white noise, or basically a random sequence. So there is some value, a lot of value in picking a very good input, so you can estimate the output. Yeah. Yeah. Any other questions? All right, so one question I am not hearing, which I was expecting to hear so far, is about L and LH, L sub F. Let's comment on that here for a second here. So, if our channel coefficients, unknown channel coefficients, are these here, where do we get this L here? Well, that's very important. Is that L equal to 2 or is it 200? The answer for this is going to depend on the propagation environment and measurements. And so the system is generally designed to operate at a certain set of carrier frequencies, certain bandwidths, and those certain bandwidths will translate into different values of L for different environments. You know, downtown Austin will have a larger value of L than will a rural place in, let's say, East Austin here. So that'll come from measurement data, and generally the system will be designed for a reasonably large value of L. Like you want to design it for an outlier case, not the average case. So the system was designed for a reasonably large value of L. Based on what's called the power delay profile measurements. And this we'll talk about in subsequent lecture, maybe around lecture number 18 or something, exactly what this is here. But I do want you to think about this here. I mean, this L is just not something we can take for granted. Now, if we were talking about a pure signal processing class, we would use a technique called order estimation. So in similar to system identification, when you're identifying an unknown, let's say FIR system, there's a set of mathematical tools that you can use to help you estimate the order of that system. So there's this AIC, minimum description length, different statistical approaches that, based on the data, will help you figure out what the right L is. So, but we're not doing system identification. We're designing a system, and for that system design, the L typically has to be kind of known somehow in advance. So that's where the L comes from here. Now, the second piece of information that is related that no one is asking about is where do we get LF here? Where does this come from? Now, this is a little bit more tricky here, and there's different ways to think about this here. So first of all, we are approximating an infinite impulse response filter. So kind of intuitively, having a big LF would be very good, right? Because then we're approximating that infinitely long filter very well. But the longer the filter you have, the more noise you're also picking up. And remember that we designed these filter coefficients based on a noisy estimate. So if you imagine that H matrix that we had earlier here, and you make that matrix longer, the noise tends to amplify even more. So generally, you don't want to pick LF to be too long. Also, the longer LF is, the more computations you have. So there's some sort of a balance in there. And so where it actually comes from, you know, it's kind of an engineering trade-off. And you would actually figure that out through probably through extensive simulations. I mean, I don't see a really sexy way to like estimate this LF. Yeah, let's think about it here. Yeah, okay, there are probably ways to do it that work on paper. I don't know they work on a real system here. So this LF here, I'm going to put that down here, probably from simulations. But a good rule of thumb is, you know, taking it approximately about 4 times L. This is just, you know, my rule of thumb here. And so if you work in engineering any kind of a wireless system, there will be some channel measurements and some channel models. So there'll be essentially statistical models for this quantity here. And these might be, like in GSM, there's models for urban areas and rural areas and suburban areas. And so you could imagine simulating all these different models, trying different equalizer orders, and figuring out which one gives you some good performance on average. And of course, you'd have to balance the different strategies, right? I mean, like we may have a channel model that corresponds to us standing on the Empire State Building. That's a very rare occurrence, so then you wouldn't want to bias it towards that event. So that's where the real engineering comes from. And you have to learn that by doing some actual engineering. All right, any questions about these two things here, L, LF? All right, let's keep going here. Oh, wait. Yes. All right. So what we're going to do right now, what we've done so far is an equalization operation. And we talked about, the ideal equalizer being an IAR filter here. So what we're going to do right now is just motivate the implementation of equalization in the frequency domain and explain why you can't just do it in a straightforward fashion. Because intuitively, you take like signals and systems, convolutions are a pain to compute in the time domain. So why don't we do it in the frequency domain? That's what we want to answer right now. And it's a relatively simple answer here. So let's see, 8, 9. So this is equalization in the frequency domain. And this is important because most of the commercial systems that we're using often, 4G, 802.11n, 802.11ac, all equalize in the frequency domain. So we're going to, in the next lecture, talk about that, how exactly that works. And so this lecture is going to motivate that particular structure here. So effectively, if we neglect noise, we've got an input-output relationship that looks like this here. Now, if you're confronted with this in signals and systems, we're in discrete time, so we take the DTFT of both sides. We get y to e to the j omega. I guess I should use 2 pi f here. I was really thinking back in 313 days there. H e to the j 2 pi f s e to the j 2 pi f here. And that looks very nice. So we could just, we have our estimate of h. So then we get out our estimate, let's say s hat e to the j 2 pi f equals y e to the j 2 pi f divided by, let's call it h hat e to the j 2 pi f here. And then we get out our symbol sequence s hat of n is equal to the inverse discrete time Fourier transform of s hat here. And from a signal processing perspective, there's no reason that this doesn't work. The problem is that we have to go through and remember what all these different operations are. So think about what is y e to the j 2 pi f here, right? That's the sum from minus infinity to infinity, y of n e to the minus j 2 pi f n here. And the problem comes in this right here. That we really have to have the entire sequence or a reasonable approximation of it to properly compute this DTFT. And in wireless, because the propagation channel is changing over time, we tend to focus on communicating information in little bursts. and then after that the channel changes. So we don't have the opportunity to send a huge block of data through this constant channel and do these calculations here. Not to mention that, what is this f here? Well, that f is a real number. How do you implement this operation? I mean, we can compute an approximation of this in LabVIEW or MATLAB, but how do you compute it exactly? Well, we'd open up Mathematica and use symbolic math, but that's not what we have in an actual chip. DSP doesn't support, Mathematica type operations. Maybe it will in the future. That would be cool, but it doesn't right now. So this is and between the two of these things here, this is probably the bigger problem. Because you could always say that, well, I'm transmitting a block of data and I insert zeros and that would be fine. But this f here is a bigger challenge here. So the basic issues, just to summarize here, so the infinite sequence, the varying impulse response, which we're assuming is linear time invariant, but it's really only accurate in a short time period. And then the fact that the f is, real number. And so what we want to do is we want to come up with a way of doing everything in the frequency domain that will still allow us to work in discrete time without having to go into the continuous frequency domain, which effectively is what this is here. This is a periodic continuous time signal. So that's the motivation for using the the DFT here. So now we're going to talk about the discrete Fourier transform. This is the one transform that was in Chapter 1 that we didn't cover because we didn't need it at the time. So we're going to talk about it now. And you should be able to calculate the DFT and IDFT and then use also this concept of circular convolution to convolve two sequences. Now I'm hoping that between 445S, 351M, that you've seen the DFT concept before, so I'm just going to review it. If you haven't, then you'll probably need to spend a little more time on the fundamentals, but I believe most everyone has seen that. So let's look now at time here. Oh, good on time. All right, so DFT. So the DFT is a basis expansion for finite length signals. So we think about this here. The Fourier series is a basis expansion for periodic signals. The Fourier transform is a basis expansion for finite energy signals. DFT is a basis expansion for finite length, I should say discrete time signals here. So the analysis and synthesis equations are nice because they're actually symmetric in some sense. The problem with the DTFT is we go from discrete time to periodic continuous time. And here, we go from discrete time to discrete time. That's convenient. And we take only a finite length sequence n and generate a finite length transform, also of length n. This is the analysis, the synthesis equations, look like this here. Again for 0 to n minus 1 here. So these are the main transform equations, synthesis, and analysis here. And then as you probably are aware here that the DFT can be computed very efficiently for select powers of n. So computed for n as a power of 2. And there are generalizations of this, so n being a prime or a power of a prime also can be computed efficiently here. So I'll put, for example, for n as a power of 2, and this is generally known as the FFT, or the fast Fourier transform. And so the computation time is, depending on if you're doing real and complex, it's on the order of n log 2 of n, instead of what would be otherwise an n squared operation. Okay, so that's a little bit about the DFT. There's two particular properties that we're going to need for the lecture number 14. So I'm going to go through those now. Hopefully you remember them by the time that lecture rolls around. The first one is the circular shift property. Because we have like a finite length signal, the main tricky thing that happens is, like, what does it mean to delay a signal? So let's look at the moment here at kind of the reverse question. What does it mean to multiply a signal in the frequency domain by a complex sinusoid? So if we have a signal in discrete time, let's say x1 of k in the frequency domain, and that's the product of e to the j 2 pi k over n times m x of k here. So notice that this is a signal in the frequency domain, and this is k here. Let me see if I did that right here. K. Yes, that's correct here. Okay. We have the k here, the k here. We have an n here. If you don't have an n here, this doesn't work. And then that gives us, in the time domain, this x1 of n is equal to x of n minus little m here, modulo n, for 0 less than or equal to n, less than or equal to n minus 1. And because the signal is finite length, we always treat that, x1 of n is, strictly speaking, is undefined outside the interval 0 to n minus 1. Sorry, that should be x of, doesn't matter, x of n, anything here. So the important observation here is that this right here, this is a modulo by capital N here. So what it means is that circular shift plays the role of linear shift in with the DFT here, right? So if I take a sequence here, so if I had a sequence that went 1, 2, 3, etc. here, up to 7, and then I was to shift that, then I would get 7, 1, 2, ... 6, and that would correspond to x of k, and then this would correspond to, let's see, that's going to be e to the j 2 pi, what do I have here, 7 k over 7 times 1 here. So that's the first important property here, circular shift. So again, that's like modulo n. So if this is like, 1 minus 7 giving us minus 6, modulo 7, that would give us 7 minus 6 is 1. Right, any questions about circular shift? All right, second property that we need is the circular convolution. And so that is essentially that, let's go back and look at products in the frequency domain here. So suppose I have two length n signals, and in the frequency domain I multiply them together, creating this right here. So it turns out that in the time domain, this is equivalent to y of n is the sum from L equals 0 to n minus 1, h of L, s of n minus L modulo n here. And this is also equal to somewhere n, 0 to L, s of L, h of n minus L modulo n here. So this is called circular convolution. And so what's important here is that you're summing from 0 to n minus 1, and you're summing always products of both of these two signals together. So there's no edge effect here. And the typical way that the circular convolution is visualized, using the equivalent of the flip-in slide is a barrel of all things. And so you have like these two concentric rings here. So let's call this S of 0, S of 1, S of 2 here. And you go through here and you turn the lock this way here. And so then you get like y0 equals S0 H0 plus S2 H1 plus S1 H2, y1 equals S1 H0 plus S2, S0 H1 plus S2 H2, if I did this correctly here, and I may be doing it completely wrong. 0, 1, S2, H0 plus S1, H1 plus S0, H2 here. So that's just a standard circular convolution here. Okay, so we will need to keep in mind this circular convolution property and the circular shift property when we want to do equalization here. And the key idea that we're going to exploit in single carrier frequency domain equalization and in orthogonal frequency division multiplexing is that we're going to modify the transmitted signal so that we can convert a linear convolution into something that looks like a circular convolution. So the idea is going to be that we're going to use at the receiver and possibly also the transmitter some DFTs. So we can do the equalization in the frequency domain. And what we've got to do is we've got to get rid of the effects of this modulo here to make this look like a linear convolution. And so we'll see the main trick for that. There's several different ways to do it. The one that we're going to use is called the cyclic prefix. And so that's what we're going to do on Wednesday. So we're going to cover the cyclic prefix and then show how to do this equalization purely at the receiver and also jointly at the transmitter and receiver using the DFT. So to summarize here, what we've done today so far, let's see. So we talked about least squares channel equalization. So the objective here was to estimate the equalizer coefficients from the estimate of the channel. And then we took kind of a detour here and showed that, by the way, we can estimate the equalizer directly from the training data. And then we explained why the frequency domain equalization is hard. DTFT just not suitable for these kinds of calculations. And then finally, we motivated the DFT. And so you should be able to calculate these DFTs and circular convolutions. And also you will need to know the properties in the tables if you don't know them already. So you will need to know how to use the DFT in other problems as well. All right, that's it.